Okay, so welcome everyone to the problem solving session for week 7 of the course Computational Competitive Algebra. So I am supposed to solve some problems uh, based on the contents of week 7. So first let's list down the topics of week 7. So I will just write down the keywords. So we started with integral homomorphisms and integral extensions. So integral extensions of rings, integral extension. Uh, then we studied some properties of integral extensions. Like if we localize a integral extension, we will still get a integral extension. And if we go modulo by a contracted ideal, again we will still get integral extension and some other properties. Uh, then we have defined, we have seen that in a ring map, the set of all integral elements forms a subring, and that we have called as integral closure. And after that, we have defined integrally closed rings. Integrally closed rings. And then we move on to the famous theorems known as Noether normalization lemma. And using that we have proved several versions of Hilbert and Alstelenza and equivalence of those things. So Hilbert's and also other consequences of Noether normalization lemma. So Hilbert's Alstelenza, and then we have defined the height of an ideal. So first we have defined height of a prime ideal, then using that we have defined height of an ideal, and then we have defined the full dimension of a ring, so which is basically the topological dimension of the prime spectrum of the ring. And then we proved some theorems. So basically how prime ideals behaves with integral extensions, so theorems related to that thing. So let me write down as integral extension and prime ideals. So behavior of prime ideals under integral extension. So integral extension and prime ideals. So basically the theorems we have seen are lying over theorem, and the incomparability theorem. And after that we spend some time on the going up theorem. So there is something also known as going down theorem, but I don't think we have done that in those lectures of week 7. So going up theorem. And after that we have particularly mentioned about the dimension of polynomial rings, or in particular dimension of finite generated algebras or affine algebras, dimension of polynomial rings. And in the end we have defined what we called as Artinian rings and modules. So Artinian modules, and we have seen some examples, and maybe we have seen some one or two properties. So let's write properties. That's all. So these are the topics of week 7. So let's start solving some problem based on these topics. Yeah, okay. Okay, so let's start solving some easy problems to get a good flavor of the topics. So let's start with height of ideal. Uh, so let R be a principal ideal domain, which we denote write PID as a sort. So let R be a PID which is not a field, which is not a field, and let I be an ideal of R. Let I be an ideal of R. Okay, then what are the possibilities of height of I? Then what can you say about, we denote height of I by just ht of I. So what can you say about height of I? So uh, I is any ideal in a PID which is not a field, because in a field we have only two ideals, 0 and the whole ring. So we have only two choice. But so that's why we are assuming R is not a field and I is arbitrary ideal. So what can we say about height of I? Okay. So first of all, it's a PID. So every ideal is principal ideal. So I is also principal ideal. So since R is a PID, so I is generated by some x. So for some element x of R. So let's recall the definition of height of I. So now height of the ideal I is basically minimum of height of P such that P belongs to V of I. V of I means the set of all. Okay, so I will write here V of I is basically all those prime ideals of R such that P contains I. So we need to check height of this prime ideals P which contains I. So basically we need to look for height of prime ideals. So we need to check the possibilities of height of P where P belongs to spectrum of R. Means P is a prime ideal of R. So we need to check height of prime ideals in a principal ideal domain which is not a kid. So in a principal ideal domain, so what are the possibilities of prime ideals? So since R is a PID, then every non-zero prime ideal is maximal. So this is well known. So every non-zero prime ideal is maximal. This is the first thing. So okay, so let me write down here. So this is the first thing that so every non-zero prime ideal is maximal. And second thing is, uh, if you take a non-zero prime ideal, a non-zero prime ideal, let's say P, okay, we don't need to put any name. Every non-zero prime ideal, we already know it is a principal ideal, but it is generated by an irreducible element. So every non-zero prime ideal, uh, okay, we don't need that fact. Okay, so this is the only thing we need to know. So let P be an arbitrary prime ideal, and we need to know the height of P. So we can separate it in two cases. See, suppose P is 0. So if P is 0, then so the only chain which is ending at the 0 is the singleton set 0. Means all this has to be 0 ideal, because we will not get any chain. So height of P has to be 0. So height of P has to be 0. Now let's assume P is non-zero. Then we need to find a chain of prime ideals ending at P. So we need to find maximum possible length of chain of prime ideals ending at P. So that is the height of P. So if this is a chain of maximal length ending at P, then this n is the height of P. So you need to find those chains. So if P is non-zero, then definitely 0 is proper subset of P. So this is a chain of prime ideals. Now, can there be any other prime ideal between 0 and P? Now, if Q is non-zero, okay. Now let Q is non-zero prime ideal and 0 subset of P subset of Q. So can we have a chain like this? We cannot have, right? Because every non-zero prime ideal is maximal. So Q is itself maximal. So Q has to be equals to P, or uh, Q has to be equals to P. But this is not possible, because Q is maximal. So 0 subset of P is only chain of prime ideal chain of prime ideal ending at P. So height of P is exactly equals to 1. So this implies height of P is exactly equals to 1. So we got height of all possible prime ideals. If it is 0 prime ideal, then height is 0. If it is non-zero, then height is 1. Now let's come back to arbitrary ideal. So now if I is 0, then I is itself a prime ideal, then height of I is definitely 0. And if I is non-zero, then definitely I is subset of some maximal ideal. And this is all the non-zero prime ideals are maximal. So this implies height of I will be same as, in this case, height of M, and there will be unique maximal ideal containing I. So height of M, which is 1. So height of an arbitrary ideal is either 0 or 1. If it is a 0 ideal, then height is 0. If it is a non-zero ideal, then height is 1. So that are the only possible choices in case of a PID which is not a field. So from this, we can also conclude that dimension of a PID is 1. So note that, so dimension of a PID which is not a field is 1. And if it is a field, then its dimension is 0. Okay. Okay, so let's move on to another problem. So problem number 2. Okay, let R be a non-zero ring. So R not equal to 0, be a ring. Then prove the following. Prove the following statements. So first one is the dimension or the crude dimension of R is 0 if and only if every prime ideal is maximal. So dimension of R is 0 if and only if every prime ideal is maximal. Now the second one is how this dimension behave with localization. So dimension of the localized ring S inverse R is always less equals to dimension of R for any multiplicative subset S, multiplicative subset S of the ring R. And the third one is how this crude dimension behave with quotient rings. So dimension of the quotient ring R mod I is less equals to dimension of the original ring R. This is for every ideal I of R. Okay, so we have three statements. First one is dimension of R is 0 if and only if every prime ideal in R is maximal. So this is if and only if. And the last two statements are about how dimension behave with localization and how this dimension behave with taking quotients. Okay, so let's prove these things one by one. So these are all easy statements, but it's worth to remember. So let's prove the first one. So this is a if and only if statement. So we need to prove two things. So suppose dimension of R is 0. So dimension of R is 0 means the maximum possible length of chain of prime ideals like this is 0. Means that this n has to be 0. So if P is a prime ideal, so let P be a prime ideal. We need to prove that P is maximal. So if P is not maximal ideal, then P must be contained in some maximal ideal. Then there exists a maximal ideal, let's say M, such that P is proper subset of M. But then we are getting a chain of prime ideals of length 1. But then this implies, so dimension has to be at least 1. Dimension of R is greater equals to 1. But this is a contradiction because dimension is 0. So this is a contradiction. So P is a maximal ideal. And the converse, so one side is proved. Now conversely, if every prime ideal is maximal, then in a similar manner you can show that the only possible chain of prime ideals is singleton chain. Just single prime ideal will be there in that chain. So dimension has to be 0. So then, so I will write it clearly. Then clearly, dimension of R is equals to 0. So this part is very easy. So first part is done. Now let's do the second part, the behavior of dimension with localization. So B. So let S be a multiplicative subset of R. So so for that now, okay, so we need to check the behavior of dimension and prove this inequality. So suppose P0 proper subset of P1 proper subset of dot dot Pn be a chain of prime ideals in this localized ring S inverse R. But how this prime ideals looks like? So recall that. So what is prime spectrum of S inverse R? So how this is related with prime spectrum of R? So this is basically extension of all those prime ideal P such that P is in spectrum of R and P intersection S is empty. And there is one correspondence between these sets. Right. So this is something we have seen in the lectures. So we will get prime ideals, and this is not only one correspondence, this is also order preserving. So we will get prime ideals pi of R such that S inverse pi is basically capital Pi for all 1 less equals to I less equals to m. And we have P0 proper subset of P1 dot dot proper subset of Pn, a chain of prime ideals in R. So, if this one is a chain of prime ideals in S inverse R, then corresponding to this we are getting a chain of prime ideals in R of same length. So if this one has maximum possible length, so this one is also a chain of prime ideals, but this chain can have much more prime ideals here. So what I am saying is, thus for every chain of prime ideals in S inverse R, we will get a chain of prime ideals of same length in R. So here we have S inverse R. Sorry, here we have R, and here we have S inverse R. So here if we get a chain, then we can contract it back to get a chain of prime ideals in R. So if we take maximal possible length here, then the same length, then we will get a chain of prime ideals of same length here, but this may not be maximal possible length. We can add much more prime ideals here. So this dimension has to be less or equal to R. So clearly dimension of S inverse R is less equals to dimension of R. So the second one is also done. Now the third one. So third one is behavior of dimension with taking quotients. So this is also similar to the second one. So I will just write the reason and not go in much detail. So C. So let I be an ideal of R. Then recall that what is prime spectrum of R quotient I. This is basically P quotient I such that P belongs to spectrum of R and P contains I. So this is also one so this set is in one order preserving correspondence with the set uh, just set up all prime ideals P such that P belongs to spec R and P contains I. So this is the correspondence theorem. So again, by the similar reason as in B, for every, so here you have I, here you have R mod I. So again, for if you take a chain of prime ideals here, so it is like so it is like P0 mod I, proper subset of P1 mod I, proper subset of Pn mod I. Then this chain will give you a chain of prime ideals in R, like P0 proper subset of P1, proper subset of Pn. And this chain actually contains I here. Here it is contains I. But we can add some more primes which is contained in I. So those will not contribute prime ideals in R mod I, but they are prime ideals in R. So, so if this one is of maximum possible length, here we also get a chain of same length, but this is not, this is may not be maximum possible length. We can add some more primes here. So similarly, dimension of the quotient less equals to the dimension of the ring. Okay, so this is also not difficult, just a fact, just a fact. So if you use the correspondence theorem. Okay, so now let's see some examples how to find the dimension of some polynomial rings or some algebras, fine algebras. So this is problem number 3. So find the dimension of the following rings. Dimension of the following rings. Okay, the first one is kx square xy y square, this one, and the second one is kx y z modulo the ideal xy generated by xy and xz. So only these two. So we need to find the crude dimension of these two rings. So how to do that? So we will use some results from the lectures. So recall that crude dimension is basically maximum possible length of chain of prime ideals. So that is the definition. But using the definition, it is very difficult to compute the dimension. So that's why we have to use some results. So note that this ring R, okay, let's say it is R, k x square xy y square. So then you can easily see that this is a subset of kxy, the polynomial ring in two variable x and y. So this is a sub algebra of kxy. And also note that both x and y are integral over the ring R, because if you take the polynomial t square minus x square, so this is a polynomial in R of t. This okay, because x is a root of this monic polynomial t square minus x square. Similarly, y is also root of t square minus y square belongs to R of t. So both these elements are integral. That will imply R subset of kxy is integral, because every x and y are integral. Since x and y are integral, that will imply all elements in kxy are integral. So this is an integral extension. So this is an integral extension of rings. Now recall that if we have an integral extension, then dimension of both the rings has to be same. So that will imply dimension of R is same as dimension of kxy. This is from the lectures. But what is dimension of kxy? So this is so we have two variables. So this is dimension of k plus 2, but k is a field, so dimension of k has to be 0, so it is actually 2. So dimension of this ring k x square xy y square has to be 2. So the reason is we have this integral extension. Okay, now let's do the second one. This dimension of this quotient ring. So B. So again, let R be the ring kxyz modulo x ideal generated by xy comma xz. So we need to find dimension of R. So one thing, okay, let me mention it here. So so for a ring R, dimension of R is basically same as maximum of, okay, not maximum because it may be infinite, so supremum of dimension of R mod P such that P is a minimal prime of R. So this is one observation which you can try to prove because it's very easy. Because what is dimension of R? It is chain, maximum possible chain of length of prime ideals. So this P naught has to be some minimal prime. So this chain has to start from some minimal prime. So this chain will correspond, say, chain of prime ideal in a quotient ring like this, where this denominator is a minimal prime. So there will be one correspondence. So we need to take supreme. So let's use this one. So let's try to find the minimal primes of R. So that means minimal prime divisors of this ideal. So 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 let's find minimal primes of R. So it will be just minimal prime divisors of this ideal. So we need to find the primary decomposition of this ideal. So it is xy comma xz. So now Now if P is a prime ideal of kxyz and P contains xy comma xz, then what can we say about P? Then that will imply xy belongs to P and xz belongs to P. So this will imply x belongs to P or y belongs to P. This is one statement. And x belongs to P or z belongs to P. So from these two statements, we can either say that either x belongs to P or y comma z both are in P. So that will imply either x subset of P or y comma z subset of P. So I am not using primary decomposition. So these two are minimal primes of this ideal. So that will imply minimal primes of R are basically the okay. So ideal generated by X modulo ideal generated by xy comma xz and ideal generated by y comma z modulo the ideal generated by xy comma xz. So we have two minimal primes of R. So dimension of R is supremum of dimension of R mod P such that P is minimal prime of R. So what are the dimension of R mod P? So R mod, so let's name this one. Let's put this as P1 and put this as P2. Now what is R mod P1? This is basically kxyz modulo ideal generated by xy comma xz again modulo by ideal generated by x modulo xy comma xz. So if you use third isomorphism theorem, then this is basically kxyz modulo ideal generated by x, and this is basically isomorphic with ky comma z. So R mod P1 basically isomorphic to ky comma z. So that will imply dimension of R mod P1 is same as dimension of ky comma z, and again as we have done in the previous problem, this dimension is 2. Now what about R mod P2? So R mod P2 is same as kxyz modulo the ideal xy comma xz again go modulo by y comma z modulo xy comma xz. So again use the third isomorphism theorem. Then this is basically kxyz modulo ideal generated by y comma z, and this is simply kx, right? So uh, so this will imply dimension of R mod P2 same as dimension of kx, and this is basically 1. And since it is the supremum of 2 and 1, so dimension is has to be 2. So hence dimension of R is equals to 2. Okay, so I hope it's fine. So you just try to prove this one. This is not at all difficult. So, or you have just to observe this. So we have using the results, we have found this dimension is 2 and also this dimension is 2. Okay, so I forgot to mention one thing, that here we have proved that dimension of R is 0 if and only if every prime ideal is maximal ideal. And when we have defined Artinian ring, we have proved that every prime ideal is maximal. So dimension of every Artinian ring is 0. So, so I should remark, put a remark here. So, so from A, we can say dimension of any Artinian ring is 0, because in a Artinian ring every prime ideal is maximum. So that is something we have seen in the lectures. Okay, so now let's try to see some examples and non-examples of Artinian rings. So this is what is the problem number? Okay, so this is problem number 4. So which of the following rings are Artinian? Which of the following rings are Artinian? So first one is this. Let's take the same ring, k x square xy y square. Let's take the same rings, k x y z modulo xy comma xz. Let's take c as just k x square. Let's take d as the ring of all Gaussian integers. Let's take e as kx mod x square. So we have some rings. We need to check which which of them is Artinian or not. So solution. So for the first two, we can say directly from the previous theorem. So A and B are not Artinian because their dimension are not 0. So their dimensions are 2, that we have already seen. Also, we can say that here these rings has some prime ideal which is not maximum. Okay, so like okay, let me write down here. Also note that the ideal x square y square is okay, not this one. Note that 0 is a prime ideal because it's an integral domain, k x square y square, but not maxima. And also in the second ring you can see that the ideal generated by x modulo xy comma xz is prime but not maximum. So these two rings are definitely not Artinian because their dimension is not zero. That is the first thing. So they cannot be Artinian, or otherwise we can give the reason as it contains some prime ideals which are not maximum. Now what about the third one, kx square? So again, you can see that this is a subring of kx and this is integral extension. So this will give this dimension is 1. So it is not Artinian. And again, you can also see that 0 is prime ideal but not maximum. So it is not Artinian. So this is also not Artinian. Now what about Zi? Zi is Artinian or not? So again, the same reason that Jedi is an Euclidean domain, but not a field. That we know, but not a field. So Euclidean domains means PID. So Jedi is a PID, but not a field. So so 0 is the prime ideal, which is not maximum. So dimension of Jedi is also 1. So this implies Jedi is not Artinian. So the only option is the last one, so it has to be Artinian. So thus kx mod x square is Artinian. So we are doing this by eliminating the options, but you can do it but you can check it also. So its dimension is 0, that you can check by the earlier methods that I have mentioned, and also it is Noetherian. So Noetherian and dimension 0 means Artinian. So that is something you may be going to see in the next lectures. And okay, that's all. So the last one has to be Artinian. Okay, let's move on to the next problem. So maybe it is yes, problem number 5. So let R comma M be a Noetherian local ring. So R comma M be a Noetherian local ring. So R is a Noetherian ring and M is the only maximal ideal in R. Then prove that exactly one of the following two statements can hold. So the first statement is, so exactly one of the following two statements can hold. So the first statement is m power n equals to 0 for some n, and otherwise m power n is not equals to m power n plus 1 for all n greater equals to 1. So either some power of the maximal ideal is 0 or m power n is not equals to m power n plus 1 for any positive integer n. So either one of these two statements can happen in a Noetherian local ring. So how to prove this? So we need to prove if this statement does not hold, then this statement has to be hold. So suppose the B does not hold. So that means m power n equals to m power n plus 1 for some n greater equals to 1. Now that implies m power n equals to m times m power n. But we are in a Noetherian local ring. So this m power n is finitely generated and m is the Jacobson radical. So m power n is finitely generated and m is itself the Jacobson radical of R. So by Nakayama's lemma, this m power n has to be 0. So we are assuming B does not holds, then we are proving that A holds. So this implies A holds. So either one of these two statements can hold. And also I will put remark that so this problem says that if you have a Noetherian local ring, then this has only two types. Either some power of the maximal ideal is 0 or m power n is not equals to m power n plus 1 for any n. So in the first type, it has to be an Artinian local ring. So let me put that as remark. So a Noetherian local ring R comma M such that m power n is 0 for some n greater equals to 1 implies R is Artinian local ring. So its dimension is 0 and it is Noetherian, so it has to be Artinian. So you will see this statement in the upcoming lectures. So R is Artinian local ring. Okay, so this is something very easy fact by from the means I mean it is very easy conclusion of the Nakayama's lemma. Okay, so now we can move on. Okay, now let's solve some problems based on the other topics. So it is problem number 6. So we have already defined integrally closed rings. Okay, now we will see something particular case. So that so that an UFD means unique factorization domain, and UFD is integrally closed in its fraction field or field of fractions. So we need to prove that an UFD is integrally closed in its fraction field. Okay, so let's start with an UFD. So let D be an UFD, and let's say K be the fraction field of D. So then we have a ring homomorphism from D to K. We need to prove that D is integrally closed in K. So that means no elements of K other than D are integral over D. So we need to prove that D is integrally closed in K. So that means no other elements, no elements of K. Okay. So no, that means no elements of K other than D is integral over D. So that is what we have to prove. So how to do this? So we have the ring map here, like R goes to R by 1. So let's prove it by contradiction. So suppose uh, let's say R by S belongs to K but not in D is integral over D. So we are taking an arbitrary element of the fraction field. So which has this form R by S. So we can assume that the GCD of R comma S is 1 because R and S, these are elements of D, and D is unifactorization domain. So we can talk about the GCD of those elements. So we are assuming that GCD is 1. So we cannot cancel out this numerator and denominator. Now this is integral. So there exist A1 up to AN belongs to D such that R by S power N plus A1 R by S power N minus 1 plus AN minus 1 R by S plus AN equals to 0. So R by S is integral over D. That means it satisfies some integral equation over D. Means it satisfies some monic polynomial over D. So now, so if we clear the denominators, so then we will get R power N plus A1 R power N minus 1. So let's multiply this equation by S power N in the both sides. So s power n minus 1 plus dot dot a n minus 1 r s power, okay, this is just s, n minus 1 plus a n times s power n equals to 0. Now all these terms involves s. So let's collect these terms in one side. So r power n equals to minus of, okay, let's take s common. So then a1 r power n minus 1 plus dot dot so on a n s power n minus 1. Now s divides the right hand side. So this will imply s divides r power n. So if p is a prime such that p divides s, then p will divide r power n, and that will imply p will divide r. So that will imply GCD of r comma s is not equals to 1 because p is there. So this is a contradiction. So we are getting a contradiction. Uh, that means what we have assumed is not correct. So what is not correct? So we have assumed that there exists an element r by s which is in k minus d but is integral over d. So that is not correct. So hence d is integrally closed in k. So d is an unique factorization domain. That means so it has to be integrally closed in its fraction field. Okay, so let's see a specific example. So one easy example is Z. So Z is PID. That will imply Z is UFD, and its field of fraction is the rational numbers. So this will imply Z is integrally closed in Q. So this is well-known example. Now the second one is, let's take R as Z root 3. So clearly this is an integral domain because it lies between Z and Q. And what about is its fraction field? So Q of R, the field of fraction. So let's put it as K. So this is basically Q round bracket root 3. So is Z root 3 integrally closed in its fraction field? So, so how to check this? So define, let's say n from r minus 0 to z by n of a plus b root 3 as modulus a square minus 3b square. Then you can check that R is an Euclidean domain with uh, where this n is an Euclidean valuation or Euclidean valuation function. So you need to check that for to check it's an Euclidean domain, you need to check that with respect to this function, we can do the division algorithm or Euclidean algorithm here. So that is the main thing. So that you can check the axioms. That is very easy actually. It's just a routine check. So this ring is actually an Euclidean domain. So thus Z root 3 is an UFD. So it has to be integrally closed. So I am leaving these checkings to you. So you must have done these things in earlier courses of ring theory, but it's a good time to recall those things. So okay, so it should be n, I guess. Yeah, but one needs to be careful here. If you take root 5 instead of root 3, then a similar type of function will not give you an Euclidean valuation, because z root 5 is not an Euclidean domain. So similar things will not hold there. So you have to be careful. So these are two examples. Obviously, polynomial ring in one variable or polynomial rings over fields, those are also UFDs. So those are also integrally closed. Okay, let me put that. So a x1 up to xn is UFD. That will imply it is integrally closed in its fraction field. Okay, so let's do some problem related to Noether normalization. So it is problem number 7. So this is from the practice problem set. So let P be a prime number then find an example of a finitely generated so find an example of a finitely generated AP algebra. So AP is basically the field on K elements. So AP algebra that does not have a Noether normalization that does not have a Noether normalization consisting of linear polynomials. So I will explain what does this question wants to say. So let me write it. Let me complete it. So does not have a Noether normalization consisting of linear polynomials. Okay, so to understand this problem, First, let's recall the Noether normalization. So if you have a field K, so K be a field, and suppose R you have a finitely generated K algebra, then you can find x1 up to xn belongs to R, such that x1 up to xn are algebraically independent over K, and if you take this, so this behaves like variables, so if you take this polynomial ring, then you have a inclusion map this polynomial ring to R, so this is finite, in particular integral. This extension is finite, in particular integral. So this is what Noether normalization lemma says. So I will write it as NNL, Noether normalization lemma. So we basically say this polynomial ring as Noether normalization of R. So this one we call as Noether normalization of R. Okay. Now when this field K is infinite, then we can choose x1 up to xn as linear combination of the algebra generators of R. So R is a finitely generated K algebra. So it has a finite generating set as algebra. So we are saying that this x1 up to xn can be chosen as linear combination of those generators. So when K is infinite, then we can do. So this is from the proof is same. But here we are saying our field is FP, which is finite field. So that's why they have told to find an example where we may not find linear polynomials, which gives a Noether normalization. So recall from the lectures, there we have seen one example. So we will try to get some example from there. So recall in Z2XY, okay, in R equals to Z2XY and I is the ideal, uh, x square y plus xy square. So if we take R mod I, then it is a finitely generated Z2 algebra, and it does not have any Noether normalization, Noether normalization consisting of linear polynomials. And how we have conclude this thing? So because every k automorphism of this ring Z2XY, which fixes Y, also fixes I, also fixes the ideal I. So so we will not get any polynomial with a power of y as a term. So that means that y polynomial with a power of y. So we will not get any polynomial with a power of y. That means y will not be integral over that ring. So it cannot be integral extension. So this is for Z2. So for p equals to 2, we already have an example. So for any prime p, let's take the ideal I. So here we have taken x square y plus xy square. So let's take x power py plus xy power p. So here we have to check for all automorphisms and check that for all uh, here k means p automorphisms of fpxy which fixes y and x maps to some linear polynomial maps to x plus lambda y, where lambda belongs to fp minus 0. So these are the all automorphisms that we need to check. Also fixes the ideal I. So here also we will not get any uh, polynomial in y, any polynomial which has a term as power of y. So okay, let me write those automorphisms. Phi of lambda from fpxy to fpxy, where y maps to y and x is mapping to x plus lambda y, and check phi lambda of the polynomial x power p plus y plus xy power p. Okay, let me check that. It will not take much time. So what this is, x is mapping to x plus lambda y. So this is x plus lambda y power p times y. Okay, sorry, we need to take minus. That's my mistake. So let's take minus here. So earlier we have taken plus here, but we are in Z2. In Z2, minus 1 and plus 1 are same. So this is minus x plus lambda y times y power p. But we are in FP, which is characteristic P. So this thing will be same as x power p plus lambda power p times y power p times y minus x y power p minus lambda y power p plus 1, and lambda power p will be same as lambda. So this is because in a p, lambda power p minus 1 is equals to 1 from the Lagrange's theorem in group theory, because its multiplicative group has order p minus 1. So lambda power p is equals to lambda. So it is x power p plus lambda y power p plus 1. Okay, x power p times y minus x y power p minus lambda y power p plus 1. So this term and this term will cancel out, and we will get x power py minus xy power p. So phi lambda of I will also be same as I. So we will not get any polynomial which has a term as power of y. So this example will work. Okay, now let's do some other problem. So this is problem number 8. So consider the integral extension z to z root 5. Okay, let's put phi. Then find some prime ideal p of z root 5 which lies over or lying over the prime ideal 5z of z. So what does it mean? Okay, let me explain. So here you have a ring map from z to z root 5. It is phi. Now it will induces a continuous map from z root prime spectrum of z root 5 to the prime spectrum of z. So let me call as phi star. Now here you have taken 5z. So we need to find an ideal here P which maps to 5z under phi star. So we need to find some prime ideal P of z root 5 such that phi star P is equals to 5z. But what is phi star P? That will imply phi inverse P is equals to 5z. So we need to find some prime ideal here which contracts back to 5z. So one easy guess is take P is equals to the ideal generated by root 5 in Z root 5. So how these elements look like? So this is A plus B root 5 times root 5 such that A comma B belongs to Z. So this is same as 5B plus root 5A such that A comma B belongs to Z. So clearly, so this will imply if you take image of 5Z, this is subset of P. Okay, now what is phi inverse P? So this is n belongs to Z such that phi of n belongs to P. So all those integers in Z whose image is in P. So but the only integers is in P are multiple of 5. So this has to be 5Z. So this is clearly an example, but there might be some others. But because this is an integral extension, we will definitely get some lying over, and there are finitely many lying contractions. That is also clear. So this gives one such example. Yeah, so let's check. So we have done dimension, Artinian ring, lying over, just I have done height of ideal full dimension, I have done Northern normalization, I have done integrally closed rings also I have done, and integral extensions I have already used. So basically I think I have covered all the topics. So let's stop here for today. So again we will meet in the next week.